Thanks for having me. First non-IHB speaker for this workshop. Unfortunately, I don't see the slides in front of me, so I have to look up here. So first of all, small apology. So I had to adapt the title a little bit. So when preparing the slides and the preparation for the workshop, I realized that maybe I should retarget the presentation a little bit. And so it's mainly about how to build mixed signal SoC with open source tools. Mainly based on our experience that we had pretty much in the last 2 years doing that. So here's a quick agenda, and I'll try to stick to my 20 minutes so that we have a few questions at the end. So a quick introduction, then I'll show you our open source IC design environment that we are using for our work. Then I'll present in a bit of detail one of the designs that we did. And then conclusions with also trying to outline, okay, what is missing from our point of view, which I think was also one of the questions of the workshop. So maybe before we get started, so who am I? So I'm located in Linz, Austria. So practically half of my life I have done IC design with commercial companies, with commercial tools. Mainly it was RF ICs. For cellular communication. So that's really my background. Since 2015, I'm a professor at the Johannes Kepler University in Linz. I'm chair of the Institute for Integrated Circuits there. And so my background really is analog mixed signal radio frequency circuits. I can do digital, but it's more just supporting for the other functions that we do. So my interest really started in 21, and by now, we are using open source tools pretty heavily in our electronics curriculum. So we use it for teaching, and I see a lot of benefits doing that. I'm also a founding member of the IEEE Solid State Circuits Society. So there's a technical committee on open source ecosystem, and I'm also one of the members of this technical committee. Yeah, and one thing that we do is I'm also the maintainer of the IIC OSIC tools. What this is, maybe some of you know, maybe some don't. You'll learn in a minute. And so everything I'll present today is based on these IIC OSIC tools. And like everything else, this is fully open. You can find it on GitHub. You can do pull requests to fix features, to extend it. So it's fully open like everything else. So maybe just at the beginning, so my personal belief is really that open source hardware and IC design are really important for small and medium companies, for academia, for training people. That's super helpful. But I think, giving this forum here, I think that's pretty easy sell. I guess all of you would agree on that one. So maybe some background what we also do at my institute. So we have a broad range of activities. So we do mixed signal RF in 180 nanometer CMOS. We're doing also RF millimeter wave in 28 nanometer CMOS, and also even reaching into the 300 gigahertz area in a very well-known process. That's actually your G2. So this line is all commercial. With closed source tools, commercial tools, but lately we're also doing things like this. So mixed signal designs in 130 nanometer CMOS, that is Skywater, obviously, but we will change all these activities to the IHB G2. Once it's ready, completely open sourced, open source tools, open source PDK, and also design itself is fully open on GitHub. And I will detail this design in my presentation, what we did there exactly. So everything I'll present today is either published or open, and here you find a couple of references for these works. So I hope by this I could set the stage, yeah, who I am and what my background is. And now I want to present the open source IC design environment that we did. So I think what has been perfectly clear from the talk of Sergey, when you want to do IC design, especially things like we do, which contains mixed signal pieces, digital pieces, RF pieces, you need a lot of tools. And luckily, a lot is available. So here you can see a quick overview of tools, and these are also the main tools that we use. So for semi-custom, it's pretty much the open lane open road flow for the RTL to GDS. There's also Coriolis from Europe. For the synthesis, it's Yosys. There are a couple of digital simulation tools, and then, as I said, the place and route tool based mainly on open road, open lane, and car layout. So I think digital is pretty well established. Also, custom is pretty well served in the moment, I would say. So the schematic entry that we are using is Xscheme. For simulation, we are using XICE and GSpice. Most of our layout work is actually done in Magic. So I'm a strong advocate for having Magic support as well. So I think you know that already. But also K-layout, of course. Parasitic extraction is a must. Oh, sorry, I keep mispressing. And the good thing is, what I also marked here is that in this whole tool chain, Europe, I think, has a pretty strong foothold. So a lot of these, the maintainers of these tools are based actually in Europe. So I think we're pretty well established here as a region. But here's already the problem, when you want to have really a full flow for mixed signal RF chip design, you need all those tools. So you need to download them, maybe compile them, make them work. They have to fit together. The PDKs have to be set up correctly. So it was my experience when I first got into this field, this is totally overwhelming. You simply don't know where to start. You try to compile your first package, it doesn't work, boom. And this is just a repeating experience. And even if just one tool is missing, you are stuck. So pretty soon I realized, okay, this needs improvement. And based on the original idea from eFabless, we set up to do a fully contained Docker image. So Docker image was not my first choice. I tried first with another virtual machine kind of thing, but this didn't work out properly in our coursework. But this Docker-based solution does. So actually what we do is we have one image which has a lot of tools, pre-installed, ready to work. You just download it and go. And we keep extending it. And I'll give you a list in a minute of all the tools that we have. So how can you use it? First of all, seamless. You start up this container. You can connect via VNC. Or what my preferred mode of operation is, you have just the individual windows rootless on your desktop. Works also pretty nicely. Or you can do cloud-based. I'll show you in a minute. And what also we did is we extended it from AMD 64, so your standard AMD and Intel CPUs, to ARM 64. So it runs on everything from a cloud to a Raspberry Pi. And we actually did it, so you can do chip design on a Raspberry Pi if you want. What you also can do is, we wrote a little script. It's this here. You can start up servers. You give it here a few parameters. And then the thing is, on a server, all these containers start up. And then you have individual logins with individual passwords. And then, in this example here, 4 users can just go to a specific URL. They authenticate with the password, and they can do chip design in a browser. And this is what we're going to use with our students, because I thought using a Docker image is easy enough, but there are still issues to install, especially on weak machines, older machines. So our solution is now really, we set this up for our students, and then they get the URL and the password, and they can log in and just start designing. And the data is secure, and it's on our own servers. It's backed regularly, so that's a pretty fine solution. Works very nicely. So available now. Speaking of tools, here's a list what we have currently in our image. You see it's a lot. And supporting this, we do monthly releases of our image. That's quite a bit of work, more than I have hoped. But we have to compile for 2 CPU architectures, all these tools. The underlined ones are the ones that we ourselves use regularly. But whenever I see an interesting tool, I'll add it. For example, Quarks is already included, OpenEMS, Silicon Compiler. A lot of very interesting Python packages are ready to go and already part of the package. We keep extending it. So one thing, so this is a spoiler. One thing that we are working on is we are integrating Align. I don't know who knows this package, but it does automatic layout generation. What we do is we make it nice to work. So we are not a tool developer per se, but we integrate tools that work in a way that I want to use them, honestly. So this is an X-scheme schematic, standard X-scheme schematic, nothing fancy. Here's just one include that you can do to put some constraints that you tell the layout tool. Then there is one script that you call. Essentially, you're giving it the name of the X-scheme schematic, and fully automatic you get this, a DSC and LVS clean chip layout. So it's not particularly nice. As you can see, yeah, a manual layout would be better, but it works and it was 0 effort. Yeah? So this is coming up. The only thing why it's not part of the package yet is the ARM64 build fails, and we didn't have time to debug this, and this is a recurring theme, so we had this on various tools. Yeah, the build fails deep down in the package somewhere, and then you need to debug what's going on. So once we had time to fix this, this will also be a piece of our package. Another thing that we did is a coil generation tool. We didn't find something proper, so we wanted to have a very simple tool that more or less script-based. You give it a few parameters, it does an octagonal or a square inductor, it creates the file for fast Henry, runs the fast Henry simulation, makes a SPICE sub-circuit, you're ready to go for simulation, and we even have a simple sweep for parameters. So this is in development, will also be released pretty soon. So this is now what's going on next, and I'm sure there will be further releases going on. So Align will come, the coil generation tool will come. We will, of course, properly integrate the SG13G2 once the pieces are ready. And I have a midterm goal. Besides these two, I also want to support RISC-V 64 because I think that fits the theme. And once RISC-V server hardware, compute hardware is available, I want our tools to be able to run there as well. Okay, so now what can you do with these tools? As a very quick example, I'll show you one piece. So one of the research topics at my institute is very low power chips that we use for biomedical applications. And this is one thing that we did already in the past. So this is the chip. Here's the block diagram, and here's a base station that can work with this chip to record the data and power it wirelessly. So this is all commercially done. In order to do such a chip, you need a lot of different things. You need pure play RF, like RF energy harvesting, an ultra-wideband transmitter running at 7 gigahertz. So you need RF support, you need inductors, all those things. Then you need analog capabilities, like a low noise amplifier, and then mixed signal. For example, here we put the 14-bit self-clocked SAR ADC. So this is ongoing work. We will continue and extend these activities. And to start somewhere, we tried now to focus on one of the most complex blocks, the SAR ADC, and checked whether we can do this in open source. And yes, we can. So this design now is pretty much finished. So here's a layout view of this successive approximation SAR ADC. So I cannot go into any technical detail, but I will do in 2 weeks at the Free Silicon Conference in Paris. Shout out to the organizers. So you will hear a presentation about this design in technical details. So far, it's a SAR ADC. SAR ADC, it consists of different things, like pure analog blocks, pure digital blocks, and something in between. And now, in the interest of time, I'll just quickly show what we did and how we did it. So we have, for example, full custom blocks like a comparator. So here's the design. The design entry we did in X-scheme, the layout in Magic. Then, of course, you need analog simulation. We did that in ngSpice, and then you need to do the typical DRC, LVS, and PEX. For this, we have nicely done scripts, so at least In my view, they are nicely done. Yeah, they are relatively straightforward. You just call up the script. Without any parameters, you get a help screen, and I think it's relatively straightforward to use. So this is for the full custom blocks, and then in the end, you get something like this. Yeah, so this is a comparator in 130 nanometer CMOS. It's a nice 3D rendering done in Blender, by the way. So a student of mine did this whole project, and I need to also acknowledge him. So Manuel Moser did a master thesis with me, and he did this SAR ADC design. So everything you see about this is his work coming straight from the master thesis. Okay, in order to do a good SAR ADC, you need a capacitor matrix, and to make this small and efficient, you have to custom capacitors, which rely on parasitic capacitance of the metal stack. So there is no PDK components. So in order to be able to work with that, you need parasitic extraction, because this gives you the value of the capacitor. And also then you need to convince the LVS that it works, yeah? Because there's an element in the schematic that you also need to find in the layout, which you don't with a standard extraction. So you need something like an LVS ignore. And this is the beauty in open source. So we were hitting this issue. I realized we need a feature in Xscheme. I contacted the developer, Stefan Schippers, and overnight he built the feature. I tested it, works properly. So you have now an LVS ignore in Xscheme, and now you can run an LVS on things like that. Then we also wanted to do, so this is a self-clocked ADC. Means it doesn't have an external clock. It more or less works by a ring oscillator built within the ADC. So we needed a sizable delay. You can do this with standard cells, but the design would be huge. So one other challenge that we had is making a custom standard cell. And we did. So we built a fully custom delay cell based on a weak inverter, charging a capacitor, and a Schmidt trigger. It's in the form factor of all the other standard cells, like it's conforming to the raster. We did this, of course, full custom with Xscheme, Magic, and GSpice. And then we used a Verilog gate label description, and we synthesized the layout with open lane, open road, based on standard P cells plus standard cells from the library plus standard cells that we did. So also this works. Yeah? Then, of course, plain vanilla digital design. So for all the control of this ADC, so the state machine, we have digital filters in, we have row column decoders. This is all synthesized from Verilog. For simulation, we used iVerilog and GTK wave for visualization of the results. Of course, linting is a good idea, so we did linting with Verilator. All this works, all the tools, like everything else I mentioned today, is part of our Docker and works out of the box. Of course, now you have a relatively complex design with analog blocks, digital blocks. How are you going to simulate this? Yeah? So that's a challenge by itself, because this is a relatively large block. You need to run a lot of clock cycles, since this is a SAR and we are using oversamples, so this is a lot of simulation effort. So how did we do it? So here's Xscheme, the top level schematics. Here you see instantiated the analog blocks, and here a digital block. And in order to efficiently run this, you need to do this either analog, but this would be way too slow. For pure digital, you have to write very accurate models for the analog blocks, so the way to go usually is a mixed mode simulation. And luckily, GSpice can do this. So you take your Verilog code, you synthesize it with Yosys, then there's a conversion tool which translates this from a SPICE to an XSpice format. And so we're using XSpice inside GSpice to run a full, true mixed mode simulation. Pretty cool. But this is all on schematic level. If you really want to know what's going on, you need to simulate the analog pieces on an extracted level. So we did then a parasitic extraction of the capacitor matrix and the comparator. By the way, here's the simulation result, so it really works. Yeah. Okay, before going to the final simulation, how did we integrate everything? So here we wanted to try out kind of a digital on top implementation. So we used OpenLane, OpenRoad to build the ADC. Means we gave it the Verilog code, we gave it all the custom cells, and let the OpenRoad, OpenLane tool do the placing, the generation of the power grid, and everything else. And see here you see various steps along the way. So the good thing is OpenRoad has a GUI, so you can take a look at the intermediate data. And then we extracted the capacitor arrays and the comparators. So then, I mean, it's only C extracted. Yeah. Strictly speaking, you should do an RC extract, but that's a huge simulation. So here we did a C extracted netlist. You still have 76,000 capacitors, 27,000 PSIM4 transistors. So that's quite something. And for this, we ran the simulation in XICE. And here you see a result of this mixed mode simulation on a parasitic extracted or a partially parasitic extracted netlist. So here we did even 4 conversions because we have built-in oversampling and decimation. So you see, this is a simulation that runs for several days on our strongest server using XICE, but it works and it runs. So you see, I hope you get an idea that, I mean, with all the tools that are out there, a lot is possible already. So it's not that nothing works and nothing is there. It's really working pretty well. And you can do, yeah, I would say complex blocks and designs like this. Okay, so coming to the conclusion. So based on this experience and other small things we did in the last 2 years, so what is really the big gaps from my point of view in the open source realm? So what is really needed, and Holger Vogt is there, maybe he can give me a large signal noise simulation, so this is really missing. So NOAA and GSpice, NOAA XICE do have large signal noise, and it's absolutely needed for mixed signal, whenever you have large signal operation, like in switching circuits, also when you do RF or millimeter wave, like oscillators, mixers. So this is a big, big gap which needs to be addressed. The other thing is we need accurate parasitic extraction. That's an absolute must for performing circuits. And then you have sizable netlists which you need to be able to simulate efficiently. So we need fast analog simulators. I think XICE is a good first step, but further speed up would be good. For digital, I mean, in the moment, so for academic, for first designs, I think scan insertion and ATPG is not a big issue. We usually don't do it on our designs, but once you go into commercial designs, larger digital designs, you'll need it. There's a package called Fault available, and it's installed in our Docker image, but we haven't tested it really. Yeah, with so many tools, so many individual developing teams, interface breaks regularly happen. So every month that we release our Docker, I spend usually a few days fixing everything that broke in the meantime. And of course, quality assurance is good. So only after 1 year we realized that the noise simulation of the Skyban 30 PDK of the resistors was turned off. So everyone in the world was simulating with noiseless resistors. Yeah? No one realized. Of course, if you build analog RF, that's a disaster. So we need better quality assurance of the components that we release. And I think in the end, we need something like regression suites, maybe or even overarching regression suites for various tools. And this is also high on my to-do list. So for our Docker image build, we need a regression suite just to make sure that everything works. Because in the moment, I do it manually, and that's really a pain. That's just too much work. So this needs to be automated. We need the support of EM structures, absolutely. So OpenEMS, I think, is now the tool of choice, and we have it in our image. Of course, when in the end you get S parameters or some discrete netlists, you need to be able to simulate it. So maybe we have then simulators. I think XICE maybe can do it with the harmonic balance simulation, but I'm not totally sure. So it would be ideal to be able to simulate S parameters. Magic support, yes, please, absolutely. Please give us a magic tech file for G2. Another question was, do we need a GUI for an integrated tool set? My personal view is not really. If the tools properly work, I think scripting is highly efficient. And it allows automation. Yeah, it's relatively simple to write a shell script that just does a few steps, like what I showed on the duck. I have a simple shell script which does a DRC and LVS on all the blocks. Yeah, and in the end it just gives one pass-fail. So if I have already the tools, so I'm a fan of scripting. I don't need a GUI. I would rather have good programming interfaces to the tools, like most tools luckily have. Yeah, and I think what this really lack, and that speaks to your ease of use, I see the same. The tools are developed relatively quickly, and that's a good thing. But this also means that documentation is basically always outdated. So it would be good to spend a more collective effort on up-to-date documentation, good tutorials, and well-done examples. So I think this is good for the community because people can take a look. Yeah, look inside, and what I showed on our SAR ADC, everything is in GitHub. Yeah, all the files, all the documentation, there's not a single thing missing. So if you go there, you clone it, you can perfectly replicate everything what we did. And I think if we have more examples like this, then we have something very good for the community. Thanks a lot.